Well, amazingly, here we find ourselves at the last section of the textbook where we talk about the divergence theorem. Again, one of the crown jewels of Calc 3 and multivariable calculus in general. You're going to find that this section is not actually that challenging because you've worked so hard to get to this point and you've developed all the skills that you need. You're going to find the divergence theorem is really helpful for taking challenging surface integrals and turning them into relatively simple volume integrals. In this section, the learning objectives are really just to understand the meaning of the divergence theorem, how it works, and then to apply it to compute various vectors that are, various integrals that arise in electrostatics and in flux calculations. All right, let's talk about how divergence theorem fits into these other integral derivative theorems that we're familiar with. We start with the fundamental theorem of calculus, which tells us how to integrate derivatives. And we use this one all the time when we're doing ordinary integration. We did the fundamental theorem of line integrals, which talked about path independence for certain integrands that were the gradients of scalar functions. We talked about Green's theorem earlier in this chapter, and its two forms, the circulation form and the flux form. We just finished talking about Stokes' theorem, which relates a surface integral to its integral around the boundary, its line integral around the boundary. And we're going to lift this one up a dimension. So we're going to think about the integral of the divergence of some vector field over a volume E, and we're going to relate it to the flux integral of that vector field across the enclosing surface of E. This is the statement of the divergence theorem, and it lets us take what are typically hard integrals, surface integrals, and turn them into what are typically easy integrals, triple integrals of divergence. Why does this thing work? It's very similar to what happens in Stokes' theorem, where you remember in Stokes' theorem we had all these little curls located at every point along the surface. And points that were near each other, the curls between them kind of went in opposite directions. And between the points, the curls kind of canceled. And the only thing that was left were curls around the boundary of the shape. A similar thing is happening here in the divergence theorem. Imagine that you're integrating the divergence of some vector field over some volume. At points inside the volume, let's say that there's positive divergence here, and right next to it there's some more positive divergence. You can think of positive divergence as there's stuff emanating out of that point. Well, if I have 2 points next to each other and there's stuff emanating out, the stuff between the points is emanating in the opposite direction. So there's cancellation. And if you have a nice continuous vector field F, then cancellation occurs all throughout the interior of the volume. And the only place where cancellation doesn't occur is on the boundary of the set. And that what's left turns into, amazingly, the flux integral of the vector field across the enclosing surface. There is a proof of this result that essentially relies on exactly the description I just gave you. You take the volume and you chop it up into little boxes, and adjacent boxes, here's a box and here's, say, positive divergence flowing out of the box. Well, there's a box next to it which has positive divergence because F is continuous. And so the stuff that's coming out of the top face of this box exactly cancels the stuff that's coming out of the bottom face of the box above. The stuff that's coming out of the bottom of this box exactly cancels with the stuff that's coming out of the top of the box immediately below. You chop up the volume in this way, you get cancellation, overwhelming cancellation inside, and what's left is the flux across the boundary. This proof goes through that process. And I'll leave that to you to explore. All right, another interesting result. You can imagine, again, that the divergence of a vector field is the outflowingness of the vector field at a point P. You can construct around a point in the vector field a little ball, a little sphere around the point. And you can think about the interior of the sphere, which we'll call B sub r. R is the radius of the sphere, and the boundary of the sphere, S sub r. Since the radius is small and f is continuous, the divergence of f at some point near P is approximately the same as the divergence of f at P. That's continuity. And so for all the points Q inside this little ball around P, the divergence is about the same. All right, so we apply the divergence theorem to this situation. And here we have the surface integral over the ball centered at P. And we convert it to a triple integral over the ball centered at P, the divergence of f. And we argue that this is approximately the same as the divergence of f at P, again by the continuity of the vector field. Since the divergence of f at a point P is a constant in this integral, we can pull it out, and what's left behind is simply the volume of the ball of radius r. Therefore, the flux over the surface integral can be written as just the divergence of f at P times the volume of the ball. And if we let r go to 0, this approximation gets better and better. So the divergence of f of P can actually be computed as this limit of surface integrals. Really complicated, not complicated, but interesting, intricate derivation that shows that we could use this formula to compute the divergence of a vector field at a point P instead of the traditional formula of partial with respect to x plus partial with respect to y plus partial with respect to z of each of the three components. So that's a fun little derivation. Using the divergence theorem is really just an exercise in recognizing the parts, and we'll do a lot of examples in just a moment. You're typically given a surface integral and the description of some shape and some vector field, and you convert it to a triple integral. That's almost always the direction that we go. All right, the main application of the divergence theorem is in electrostatic fields, and it's the idea of Gauss's law. This law states that if S is a closed surface in an electric field, then the flux of the electric field across S is the total charge enclosed by S. This physical law and this theorem, the divergence theorem, are so closely related that in fact the theorem, the mathematical theorem, is often called Gauss's theorem. These theorems were developed in tandem with the physics. Let me find some notes here. So this work was done by Gauss and others in the late 18th, early 19th century. Gauss, Green of Green's theorem, Poisson. The first official proof was done by a Russian, Mikhail Ostrogradsky, in 1826. And it is still important today, and it's one of the main reasons that we require Calc 3 for physics students, so that they are ready to go do electricity and magnetism, and to have this theorem at their disposal. A couple other interesting things lurking within Gauss's theorem, or the divergence theorem, is a sort of higher dimensional version of integration by parts. If you search Wikipedia for Green's identity, yes, the same Green, you will find a collection of identities, all of which flow from the divergence theorem. The one I want to draw your attention to, though there are many other useful ones, is Green's first identity, which says that if psi and phi are scalar functions, and we look at the Laplacian of phi times psi, plus the gradient of psi dotted with the gradient of phi, and we integrate over the volume, that can be written as the integral over the boundary of psi grad phi. think about what's happening here. If you look at this very carefully, you're effectively moving this derivative off of the psi and putting it onto the phi. That's exactly what you do in regular integration by parts. You move the integral off of one function and the derivative off of one function and onto the other function at the expense of these boundary terms. Same thing's going on here. I take this gradient and I move it onto the phi. The gradient, the gradient applied to this operator becomes a divergence. Together they become the Laplace operator, and what's left over is this boundary function, this boundary integral. If you take my engineering math class, we actually use that identity, but for now, let's just carry on. Let's see, I think that's most of the flyover. Let's work through some examples here. Most of these examples are pretty straightforward thanks to the power of the divergence theorem. In exercise 380, we are asked to, use a computer and the divergence theorem to evaluate the surface integral. For each, assume that n is the outward unit normal. I didn't emphasize this much in the section, but the divergence theorem involves a surface integral, and the assumption is that that normal vector of the surface integral is outward pointing. Okay, so we're asked to compute this integral, this double integral over the surface, f dot n ds, and we know that that's equal to the integral over the enclosed volume of the divergence of f dv. All right, well, let's compute the divergence of f. This is usually where things get simple. I take the partial of the first component with respect to x, plus the partial of the second component with respect to y, third component with respect to z, and I get this relatively simple scalar expression. It's probably a good idea to do this in spherical coordinates because the volume that's being enclosed is a sphere of radius 2. So we'll integrate from 0 to 2, 0 to pi, 0 to 2 pi, and we'll convert this expression to rho cosine theta sine phi, rho sine theta sine phi, and rho cosine phi. And then don't forget the Jacobian, rho squared sine, oh come on, sine phi d rho d phi d theta d theta. All right, we can do this integral over in Sage. We were, after all, asked to use a computer to do this, so let's review that, how to do a triple integral over in Sage. Don't forget to declare the variables. Here we're using rho, phi, and theta. And let's do the triple integral. We're going to integrate 3 times, like that. 2 times the quantity, rho cosine theta sine phi plus, let's see, rho sine theta sine phi plus rho cosine phi. That, I believe, is the x plus y plus z part of this. Let's close that off, times rho squared times sine phi. That is the Jacobian part of this. And now we'll begin the integration. Rho is going to go from 0 to 2. Phi is going to go from 0 to pi. And theta is going to go from 0 to 2 pi. Hopefully I got my syntax right. Let's see. Let Sage grind away a little bit, and we get 0. That was unexpected. Does that make sense? Well, let's go over to Sage again and try to visualize this surface. Okay, so I just went and copied some vector field plotting stuff from another worksheet that I have. Here we go. To do vector field plots, you have to use the plot vector field 3D command from Sage, and that needs to be, oh, and then I also want to superimpose a sphere of radius 2 on the situation. Here I'm doing the vector field x squared, y squared, z squared, because after all, that was the vector field that we were dealing with. Right here, x squared, y squared, z squared. And we're looking at this thing over a sphere of radius 2. I put the vector field plot in a variable vf, and I put the sphere plot in a variable s, and then I just show them simultaneously. Let's see what that looks like. Okay, so here's the situation. It's hard to really see what's happening unless we zoom in. If we zoom in, we'll begin to see the arrowheads on the vector fields here. Now, we were kind of taken aback by the fact that the, the net flow is 0. But if you look closely at this, you see really for every vector flowing in across the surface, if you go around the other side, there are vectors flowing out. So it's not unreasonable to think that maybe they're in complete balance. They net out to 0. And that's essentially what this is telling me. This integral represents the flux across the surface of the sphere of the vector field. We used the divergence theorem to compute it a different way as a triple integral, but we got 0. And that's that seems to be supported by the figure. All right, let's try another one. You're going to find that most of these are pretty similar, actually. They're just applications of the divergence theorem. All right, so we want to compute this surface integral where S is the solid bounded by the paraboloid z equals x squared plus y squared, something like this, right? With a flat top, z equals 4. That would be a challenging surface integral. You'd have to do 2 separate integrals, one for the paraboloid, one for the cap, and that would be a bit of work. So again, we'll use the divergence theorem. And note that this is equal to the integral over the enclosed volume of the divergence of f dv. Let's compute the divergence of f. Partial of the first component with respect to x is pleasantly just 1. Second component with respect to y is also 1. Third component with respect to z is 1. Definitely would not want to do this surface integral. That is a really messed up vector field, and it would be really complicated. This, on the other hand, I'm going to integrate over E. What kind of coordinate system are you feeling for this one? Let me go check my notes here and make sure that I remember what I used. Okay. So, feeling the cylindrical coordinate system, actually, because of the circular nature of this paraboloid. The horizontal cross sections are circular, and that suggests that we should use cylindrical coordinates. All right, so let's do that. We got triple integral. We're going to integrate 3. We have r dz dr d theta. Z starts on the paraboloid, r squared, and ends up on the plane, 4. R, let's see, what does this shape look like if we project it down into the xy plane? It's going to look like a circle of radius 2. So r is going to go from 0 to 2, and theta is going to go all the way around. Once again, we can use Sage to compute this integral, so let's jump over to Sage. And let's see, here we go. So now we're working with cylindrical coordinates. So let's declare the the cylindrical coordinates, z, r, and theta. I always just get in the habit of declaring the variables each time I start a new exercise, even if I've already declared them in the worksheet. All right, we want to integrate 3 times. And we're integrating the number 3 times r, which is the Jacobian, and r, z, goes from r squared up to 4. R goes from 0 to 2, and theta is going to go from 0 to 2 pi. And we get 24 pi. So the flux of this vector field across this somewhat challenging surface is 24 pi. The divergence theorem is your friend. All right, here we have another one where we're actually shown the shape. Let's work through this. We're supposed to compute the flux integral. Again, we're going to convert that flux integral to the divergence over some volume. Let's compute the divergence of this f. The derivative of the first component with respect to x is 3. The second component with respect to y is 1. And the third component with respect to z is also 1. We get 5. This surface integral becomes the integral of the divergence of f dv. This also looks like maybe cylindrical coordinates because we have this sort of piece of a cylinder. The cylinder is sitting on top of a quarter circle of radius 1, and it goes from z equals 0 to 1. So I'm going to go 0 to 1 in z. I'm going to go 0 to 1 in r, and I'm going to go 0 to pi over 2 in theta because it's just the quarter circle in the first quadrant. The integrand is going to be 5 times r, and then the order of integration dz, dr, d theta. And we can jump over to Sage and do this one. In fact, let's just reuse this one. We have 5r instead of 3r. We have z going from 0 to 1. We have r going from 0 to 1. And we have theta going from 0 to pi over 2. Let me just double check that. 0 to 1, 0 to 1, 0 to pi over 2. Execute 5 pi over 4. And moving right along. All right. In problem 400, we are asked to compute the net flux outward for the given surface. And in problem 400, I chose this one because I find the vector field a little bit challenging, but it's also a vector field that you encounter in physics classes all the time. Between two spheres of radius 1 and radius 2, so sphere of radius 2, sphere of radius 1 nested inside, and we're interested in the flux across that annular shell from radius 1 to radius 2. Probably going to be using spherical coordinates when all is said and done here, but the challenging part for us is what's the divergence of f? We know that we want to compute the integral s f dot n ds, and we know that that's equal to the divergence of f integrated over the enclosed volume E. So we're going to need the divergence of f. I'm going to start just by focusing on the partial derivative of the first component of f with respect to x. So we want to compute the partial with respect to x of x divided by the square root of x squared plus y squared plus z squared. Remember the quotient rule, bottom times the derivative of the top minus the top times the derivative of the bottom looks like that over the bottom squared. looking like that. I can simplify this substantially if I multiply through by this term, multiply the top and the bottom by that term. Doing so, in the numerator, I get x squared plus y squared plus z squared. A little bit of simplification here, minus x squared times 1 over, multiplying multiply the top and the bottom by the square root of x squared plus y squared plus z squared. So in the bottom I get x squared plus y squared plus z squared to the 3 halves. The numerator simplifies a little bit. The x squared cancel, and I get y squared plus z squared over x squared plus y squared plus z squared to the 3 halves. Now, based on the symmetry of these three expressions, I know that the partial with respect to y and with respect to z is going to be similar to this. So I'm going to write the divergence, the divergence of f as this partial with respect to x plus the partial with respect to y, plus the partial with respect to z. All of that over the common denominator that appears in each of the three partial derivatives, x squared plus y squared plus z squared to the 3 halves. Now, there's a little bit of simplification that can occur here in the numerator. I've got 2x squareds, 2y squareds, and 2z squareds. So that's 2 x squared plus y squared plus z squared over x squared plus y squared plus z squared to the 3 halves. And even more simplification, I end up with the divergence 2 over the square root of x squared plus y squared plus z squared. So a frightening expression to start, but the divergence turns out to be relatively straightforward. Now, I'm going to use spherical coordinates to do this integral. What integral? This integral. And I'm going to integrate over this region, the space between the sphere of radius 1 and the sphere of radius 2. What that means is rho is going to go from 1 to 2, the inner sphere to the outer sphere. Phi is going to go from 0 to pi, its full range, and theta is going to go from 0 to 2 pi, its full range, because we want the entire spherical shell. The integrand is 2 over the square root of x squared plus y squared plus z squared, which we should recognize as 2 over rho. And then don't forget the Jacobian, rho squared sine phi d rho, d phi, d theta. Get a little bit of cancellation here, and we end up integrating 2 rho sine phi d rho, d phi, d theta. And we can pump that into Sage to get the final answer. Let's do that. Declaring the variables, integrating 3 times. And remember the integrand here is 2 rho sine phi, 2 rho sine phi, and then, times sine phi. And then we integrate phi from 1 to 2. Sorry, not phi, rho from 1 to 2. Phi from 0 to pi. Looks like I've got a mismatched parenthesis here. Theta from 0 to 2 pi. And let's see if we can't figure out where that is. So that's matching the outer. That looks good. Good. This should match. Good. And that. And then this should match. Yep. All looks good. Let's run it. 12 pi. And we're done. So the challenging part here was computing the divergence and choosing the right coordinate system. Let's move on to 408. In 408, we've got a cube, but it's the same deal. We want to compute the surface integral over this cube. This would be a challenging surface integral because you have all 6 faces of the cube and you'd have to do 6 surface integrals, albeit those integrals would be relatively straightforward. Let's use the divergence theorem. So that means we can rewrite this as the integral over the enclosed area of the divergence of f. Let's compute the divergence of f. It's the partial of the first component with respect to x, 0. Second component with respect to y, 3y squared. Third component with respect to z, x. Integrating in Cartesian coordinates, because a cube is very rectangular, it's very Cartesian in nature, we will integrate with respect to x, y, and z. X goes from -1 to 1, y goes from -1 to 1, z goes from 0 to 2. We're going to integrate this integrand, x plus 3y squared, and we're going to do it dx, dy, dz. Not a terrible integral. And we can jump over to Sage and compute that integral, again declaring the variables x, y, and z, and doing the integration. We had x plus 3y squared. X went from -1 to 1, y -1 to 1, z 0 to 2, I think it was. Let me go double check. Yep. And let's run that, and we get 8. Something I want to point out here, if I get rid of the x here, it won't matter. So if I redo this integral without the x, I'm still going to get 8. Let me get rid of that x. And it's worth thinking about why, mostly because this can help you when you're dealing with complicated integrals. It can help you simplify expressions. The reason that that x doesn't matter is when you integrate with respect to x from -1 to 1, the function x is an odd function, and we're integrating over a symmetric interval. So that part of the integral is going to go away. And if I broke this up into 2 separate integrals, one for x, dx, dy, dz, and one for what remains, 3y squared, dx, dy, dz. This piece will go away because in that first integration you're going to get a 0, and that will wipe out the rest of the integration. Always keep your eye out for those kinds of simplifications. Problem 416. So here we're trying to find the flux of this vector field across the part of the hyperboloid between the planes 0 and the square root of 3 over 3. Now, it's always a good idea. Here's the surface, f dot n ds. The portion of this hyperboloid, we know that the divergence theorem applies. And it's often a good idea to, and as you've seen me do, to compute the divergence first. And here's an example of why. The partial of f with respect to x in the first component is 0, y in the second component is 0, and z in the third component is 0. So this divergence is 0, and this integral is 0, and we're done. So you don't have to think about what coordinate system to do the integration in. You don't have to worry about the surface. The divergence is 0, therefore the flux integral is 0, and we get to walk away. So always compute the divergence first when you're using the divergence theorem. Last not least, Fourier's law of heat transfer states that the heat flow vector field at a point is proportional to the negative of the gradient of the temperature. So remember that the gradient of the temperature points in the direction of maximum increase of temperature. And remember also that heat flows from hot spots to cold spots. So we can expect heat to flow in the opposite direction of the gradient. Remember, gradient points in the warm direction. Heat wants to flow in the cold direction, from hot to cold. This leads us to a really simple law, Fourier's law, and the vector field of heat flow is just proportional to the negative of the gradient of the temperature function, give or take. So heat energy flows from hot regions to cold regions. The constant is just called the conductivity, and the higher the constant is, the more quickly the heat will flow in this medium. So it's called the conductivity, and it depends on the particular material in which the heat is flowing. If heat is flowing in metal, we can expect the conductivity to be quite high, but heat flowing in a block of wood, we would expect the conductivity to be very low. The temperature function for the region is given in problem 426. Use the divergence theorem to find the net outward heat flow. All right, so we've got this temperature function. We know that the flux of heat is given by this surface integral. We replace F with its Fourier's law version, minus K gradient of T dot N, so that's where this comes from. And we want to compute this. All right, so we know that the vector field F is equal to minus K gradient of T, and we want to compute the divergence of F. And that's going to be minus K divergence of the gradient of T, which you may recall is the Laplacian of T, which you may recall is the sum of the pure second derivatives, txx plus tyy plus tzz. So it really is just up to us to compute the second partial derivatives of this function t. So let's look at the first partial with respect to x of 100 e to the minus x squared minus y squared minus z squared. That's going to be 100 e to the minus x squared y squared minus z squared times the derivative of what's up there in the exponent with respect to x. So that's a minus 2x. All right, that turns into minus 200x e to the minus x squared plus y squared plus z squared. And we want to take the second derivative. So now we take the derivative with respect to x again of this quantity. And that's going to involve a little bit of quotient rule. So we get minus 200 times the quantity x times the derivative of e to the minus x squared y squared z squared. So that's going to be e to the minus x squared plus y squared plus z squared times negative 2x plus the second times the derivative of the first. So that's just e to the minus x squared plus y squared plus z squared. We can clean this up a wee bit and get minus 200 times 1 minus 2x squared e to the minus x squared plus y squared plus z squared. And you can imagine, because of the symmetry of this function t, that the other second derivatives are going to be similar. There's just going to be a y here and a z here. So in total, the divergence is going to be, there's going to be a common factor of minus 200 e to the minus x squared plus y squared plus z squared in all three of these second partials. And what will be left behind is 3 minus 2 times x squared plus y squared plus z squared. So there's the divergence, taking advantage of this very special structure of this particular temperature function. And we're now ready to go. This is going to be spherical coordinates, and we are integrating over a sphere of radius a centered at the origin, So in rho, we're going to go 0 to a. In phi, we're going to go 0 to pi. In theta, we're going to go 0 to 2 pi. The divergence becomes negative 200 e to the minus rho squared, 3 minus 2 rho squared sine phi d rho d phi d theta. You just go check my notes, make sure I haven't made any mistakes. Oh, why are you not cooperating? There we go. Oh, I dropped a K. Good to know. So there was a K in this whole deal. I'll just put it here. Let's see, did I drop anything else? 200. Yep, that looks good. All right, maybe I have a sign error here. Let me pause for a second. Okay, yeah, I definitely have a sign error here. There's a sign that comes from the original Fourier's law expression, and then there's a sign. Notice here, I'm just differentiating the exponential part of the function, not the k. So there's actually an extra sign here. All right, it's all good. If you jump over to Sage, and I won't bore you with the details, punch this rather complicated expression into Sage, integrate it 3 times, and what you're going to get is 800 pi k e to the minus 1. I'll just make a note that that was Sage. And that's pretty much it. So the flow, the net flow across the surface is 800 pi k e to the minus 1. Does that make sense? Well, it kind of does. Let's look at this temperature function. We see that it's e to the negative x squared, negative y squared, negative z squared. So that is essentially the distance squared from the origin. As we go away from the origin, t is going down really quickly. So the further from the origin you get, the bigger this negative exponent gets, the smaller this quantity gets, and the colder it gets. So it's warm at the origin, and it's cold as we go away from the origin. Which way does heat flow? Heat flows from hot to cold. So if we're looking at the surface of the sphere of radius a centered at the origin, we would expect that flow to be positive. Heat flowing from the inside to the outside. We have an outward pointing normal, so the heat flow is in the same direction as the outward pointing normal. Another thing that you might notice here is even though we had an a in the original integral, there's no a in the final answer. Why not? Because of conservation of energy. The sphere, no matter how big or how small it is, the amount of heat energy flowing across the surface of the sphere is going to be fixed. So it doesn't matter how big the sphere is. There's only so much energy inside of it, and therefore there's only so much energy that can flow across the boundary. So you can get lots of interesting physical interpretations from these kinds of mathematical exercises. The exercises, they're all on the table, and once you've worked through enough of them, go hit the web work for section 6.8. Last web work, yay. And thanks.